This is Computational Complexity 101. If you've taken any algorithms class or anything related to do with problem solving, chances are that you would have come across many jargon terms like P, NP, NP-hard, NP-complete, and it's pretty common to actually ponder about what these classes or even terms mean. So this is me making an attempt to simplify the computational complexity classes that is thrown around at you. And let's get started. So, what is P? Uh, I'll assume you have heard of something called Turing machine. Even if you haven't, just assume it's just a crazy machine that with an infinite tape and it has like bits, symbols like zeros and ones written on it, and it has something like a head. And this, astonishingly, this crazy model, computational model that is proposed by Alan Turing, is powerful enough to simulate any computationally known problem. So it's often used as a theoretical model to study computational complexity and many other things. And I'll often be using this Turing machine. It's just enough to actually know that this is a black box of some sort, and it's okay to actually understand it as a black box for now, even if you don't know much about Turing machines. But I'll relate Turing machines to computational complexity classes, and even if you don't understand them, you can obviously refer to a less toned down definition of the computational complexity, and you will be fine. So let's get started. So what is P? P and is a decision problem, and note what is a decision problem. Decision problem is a problem with a zero or a one or a yes or no answer to it. Like, for example, is my given number a prime number? So it has a yes or a no answer to it. And note that only decision problems are associated with these complexity classes like PNP, etc. And there's also something called a search problem, and that has a different complexity class associated with it. So generally, it's often a misconception to actually ask questions like, is an algorithm like I'll be talking about the misconceptions in another slide. So let's just get started with this. So what is P? P is any decision problem, and that is solvable by a deterministic Turing machine. Deterministic Turing machine. Yeah. Deterministic Turing machine in polynomial time. So I have polynomial time here, and any deterministic Turing machine that solves it in polynomial time. And in other words, there is a polynomial time algorithm. Polynomial time algorithm is of the form n to the power c that is known to solve the problem. So this is the definition that you should be fine with if you do not have an understanding of what a deterministic Turing machine is. So an example of that would be are two numbers relatively prime. Note that two numbers are relatively prime if the GCD, the greatest common divisor of them, is 1. So uh, an example of such numbers would be 7 and 5. They're relatively prime, and you can obviously solve this in polynomial time. There is a good algorithm called Euclidean algorithm to calculate the GCD, and this problem is actually in P. Similarly, is a graph G connected? That is, can I reach from any vertex of the graph to another vertex of the graph? And that's known as the connectivity problem, and that is also in P. So, what is NP? It's a very common misconception that NP is not polynomial, and that is wrong. That is totally incorrect. And in fact, it's to do with the notation, and usually mathematicians or even computer scientists, like in my opinion, they fumble a lot of notations and they make it very hard for people like us trying to understand anything to do with them. So It's not your fault, it's just to do with the notation. And NP is actually, it stands for non-deterministic and not polynomial. So in fact, definition of NP is a decision problem is an NP if a non-deterministic Turing machine solves it in polynomial time. Note, I'm using non-deterministic Turing machine here. And a non-deterministic Turing machine, if you do not have an understanding, so anything to do with non-determinism is like, just assume you're here and you have to make a decision. And if you pick choice 1, you're here, and if you pick choice 2, you're here, and if you pick choice 3, here. Basically you have arms, and assume that you're able to clone yourself 3 times at this particular point. This is not practical and this is impossible in real life, obviously, but non-determinism allows you to do that. And so basically, the Turing machine proceeds after having made all the choices and it emulates all possible combinations. This kind of tree would be very common in recursion problems. I mean, you've heard of it, but this is what non-determinism looks like. A Turing machine is able to actually make multiple decisions at a particular point and is able to actually simulate all particular possibilities. And eventually, if there is any es in any one of the leaf nodes, the string or the problem is accepted, or it's the output of the problem is 1, that is, it's solvable or decidable. So that is non-determinism in a nutshell, not deterministic Turing machine in a nutshell. And if you do not understand that, and this has to be solved in polynomial time. So that is the definition of NP. Know that it's polynomial and it's non-deterministic, and it has nothing to do with not polynomial. And yeah, that is with the help of Turing machines. And in a nutshell, you define it something like this: NP problems take a very long time to solve. It is exponential, but these are the class of problems that are very easy to verify. And what does verify mean? To understand it easily, you can associate it, whatever I told you about NP, to a Sudoku puzzle, and know that it's very hard to solve an n cross n Sudoku puzzle. Normal Sudoku puzzles are 9 cross 9. That can be easy, but n cross n is definitely is actually a hard problem to solve. It's actually a difficult problem and it can take exponential time to solve. But hey, if I give you the solution to a Sudoku puzzle, it's fairly easy and takes polynomial time to verify that it is the solution of the given Sudoku board. So that is the definition of NP in a nutshell. And the examples of NP would be factoring large numbers. Know that this is often the basis of cryptography. The fact that we cannot quickly factorize, in fact, like get the prime factorization of a very large number, is often used as a building block to cryptographic algorithms. And we have the traveling salesman problem, and then solving a Sudoku puzzle is also known to be in NP. So, and this is the technical definition of NP. And know that it's completely okay if you do not understand this definition, but this is a definition that is actually thrown in a lot of graduate and undergraduate computational complexity courses. And this is a definition that defines NP using a deterministic Turing machine. Know that we actually defined it using a non-deterministic Turing machine. That was definition 1. Definition 2 takes a deterministic Turing machine, let's call it V, and it takes in all instances of the like all strings in the language, and it's an NP if there is a certificate Y, of polynomial length, if the certificate is of polynomial size, and V accepts Rx, which is the problem, or an instance of the problem, an instance of a string X that is in L, comma Y, which is the certificate. So it takes in both X and Y and it accepts V, and then it does it in polynomial time. So if a language L a language L is said to be in NP if there is a deterministic Turing machine V such that for all strings X that belongs to L, there is a certificate Y of polynomial length, and V accepts X comma Y and it does it in polynomial time. That is the technical definition of NP, and it's slightly not intuitive in the first glance, but it's very useful when you have to prove a lot of things, prove a problem is an NP. What you basically do is you try to get a certificate, and you just use this definition and prove that the given problem is an NP. Note that all the non-determinism is pushed to the certificate. I haven't really mentioned how you get the certificate, but essentially all the non-determinism is pushed into the certificate, and then you can use a deterministic Turing machine to actually use X and the certificate to actually accept the problem or decide the problem. At a very high level, this means that NP is a set of languages that have short proofs of membership. Short proofs of membership meaning the certificate is of polynomial length, and
it's 3 o'clock.
It can be verified efficiently. It can be verified efficiently, meaning we have a polynomial time algorithm. So this is the technical definition of NP. It's completely okay if you just understand the previous definition, and this is just for people looking for a slightly more advanced definition, and that is used in your undergrad and graduate level courses. Let's define something called coNP. Again, it's very common to actually have a misconception. In fact, let me go through the misconceptions once before actually going through what coNP is. Common misconceptions are, like I told you, NP does not stand for not polynomial. It is non-deterministic polynomial, and coNP is not the complement of NP. Again, a misconception. It's in fact, coNP is a complexity class which contains all problems whose complements are in NP. Like a language L is said to be in coNP, in the class coNP, if L complement, if the complement of the language belongs to NP. For example, the problem finding prime is in coNP because the complement of that language, the problem is basically to prove that X is not in prime, and to prove that X is not in prime, we have to prove that X is in composite, and X is a composite number, and that is again an NP problem, because to prove something is a composite number, we have to prove that it's not prime, and that is an NP. So this problem is an NP, and hence that is the definition of coNP. coNP is a complexity class which contains all problems whose complements are in NP. It is not, again, the complement of NP. Just as NP is considered to be the set of all problems with succinct yes certificates, coNP can be considered to be the set of all problems with succinct, very clear no certificates. This means that no instance of a problem in coNP has a short proof of it being a no instance. This is exactly the definition we use for NP, except for this is in this time we use it for a no certificate or a no instance. The third misconception, or very commonly used, is people ask if an algorithm that they've written is in P or NP. That again doesn't make sense, because the computation complexity classes are defined for decision problems, and note that an algorithm is not a decision problem. An algorithm is just a way to solve the problem, and it is meaningless to ask things like is BFS in P or NP. I mean, it does not have a meaning. And again, this is a question that I found in Quora, and it's asking if is finding prime numbers in P or NP. Again, this is not right. This is ambiguous because one, like, finding prime numbers is not a decision problem. Like, asking that if x is prime, that is a valid problem to ask, a valid decision problem, and that can be like, found of to be in P or NP. But again, note that if a problem is in P, it's also in NP. In other words, P is contained in NP. So if someone proves a problem is in P, it also implies that a problem is in NP. So this question is incorrect because you're asking finding prime numbers, and that is not a decision problem, and you're asking if P or NP. That means you're trying to ask if they're mutually exclusive classes, and they are not. P is in fact contained in NP. We do not know if P equals NP. That's a puzzle. That's actually something people are trying to solve. It's a mystery. But most rational people believe P is not equal to NP, but that's a story for another day. And yes, let's go, or let's define what reductions are. A is reducible to problem B if an algorithm for solving B can also be used to solve problem A. That is, if I can solve B, that also means I can solve A, because the yes instances of A can be mapped to all S instances of B, and the no instances of A map to no instances of B. So the yes maps to yes and no maps to no, and I'm trying to get a yes or no for A. So if I can go from A to B in polynomial time, note that it's a polynomial time reduction, and I haven't mentioned that, but it's reductions are of many kind, but usually the ones we define in computational complexity, there's a bound on the reduction, and you to define things like NP-complete, use a polynomial time reduction, and to go from A to B, we like if we can solve B, if there's an algorithm to solve B, that also means we can solve A, because yes of A maps to yes of B. So if we can get an answer from B, we already have an answer for A. So that is reduction from a high level. It's a much more complicated topic, and I wouldn't be covering this in depth in this video. Okay, let's try to define NP hard with the definition of reduction, since we know what a reduction is. A problem A is NP hard for every problem L in NP if there is a polynomial time reduction from L to A. Yeah, if A is NP hard, that means we can reduce every problem in NP, every problem L in NP to that problem A, which is NP hard. So the in polynomial time. So that is what this means. This will become much more clear with the help of a visualization. That means an NP hard problem is at least as hard as the hardest problems in NP. Like, let's say there are so many problems in NP, and this NP hard problem, which need not be in NP, and this problem is at least as hard as the hardest problems in NP. An example of an NP hard problem would be the halting problem. Yeah, let's define NP complete, and then let's take a look at a diagram to make the definitions clear. And a problem is said to be NP complete if it satisfies two conditions, and it's written as NPC sometimes, but that's a notation for NP complete. And a problem is NP complete if it can be both if it satisfies the following two conditions. If it is an NP, that is one, and it's NP hard. So an NP complete problem is just an NP hard problem that is also an NP. And hence, to show that a problem is NP complete, what do? We actually to show that a problem is NP complete, we actually just like need to prove that one, it's an NP, and two, all problems, all problems in NP, it reduces in polynomial time to this problem, like the problem we are trying to prove that that is an NP complete. And examples of NP complete would be 3 sat. I would advise you to read about what a sat problem is. In fact, 3 sat is just Boolean satisfiability problem, where it's more restrictive that every class can only have 3 literals, so hence 3 sat. And we have the zero knapsack problem, we have the vertex cover problem, we have clique, we have graph isomorphism. They're all NP complete problems. And please read about SAT and Cook-Levin theorem. Cook-Levin theorem in a nutshell is just like the first NP complete problem that is proven, and that is satisfiability problem, the SAT problem. Hence, we know that 3 SAT is NP complete. And why is this useful, you may ask? This is useful precisely for this reason, to prove that a new problem X is NP complete. So, how do you do this? First, you need to prove that X is an NP, and second, you need to prove, take an already known NP complete problem. This is the result of Cook-Levin theorem, and we reduce that 3 SAT problem in polynomial time to X, to this problem. We are trying to prove that is NP complete, and thus X is an NP complete. Note that it need not be 3 SAT, it can be any known NP complete problem that we've already proven to be NP complete. We can proven to be NP complete. We can use that result to actually reduce in polynomial time from that known NP complete problem to our problem, and then we can prove that X is NP complete. Okay, how do we prove that a problem A is NP complete? We can prove that A is NP complete by picking any problem that is already proven to be NP complete. And because to show something is NP complete, we need to prove that every language that is in NP, x1, x2, x3, and so on up to xn, is in NP, and that reduces to our problem in polynomial time, and that can be pretty hard to do. Instead, we already take a known NP complete problem. This is the result of Cook-Levin theorem, and someone already did the work for us. Hey, why not use that? So this makes it much simpler, because since we already know that 3 SAT is NP complete, that means every problem in NP can be reduced in polynomial time to 3 SAT. And if we can show that 3 SAT can be reduced in polynomial time to our problem A, that's the only chunk of work we need to do. And this also implies that every problem x1, x2, x3, and xn, which is in NP, is actually reduced in polynomial time to our problem A, and that is the definition of NP complete. So that's the definition of NP complete, because A is an NP, that's condition 1, and condition 2 was that every problem x1, x2, x3, and so on up to xn, every problem that's an NP is also reducible in polynomial time to our problem A, and hence A is NP complete. So this is how you prove a language A or a problem A is NP complete, by actually picking any problem that's already NP complete. And in our case, we picked 3 SAT, and we just prove that 3 SAT reduces to A in polynomial time. And once we do that, our proof is done, and we can show that A is NP complete. Okay, I want you to pause for a second and think if we can actually define something like, what is coNP complete? We talked about coNP, we talked about NP complete. And can you pause for a second and think what can be the definition of coNP complete? This is because it's often very common to define things like C hard, C complete, etc., where C is the computational complexity class. Like people talk about what is P complete, what is for a lot of classes, like for example, what is NL complete. So many extensions are the same, and they follow the exact same template. One, you have to prove that for a language to be C hard, you just need to prove for a language to be C complete, you need to prove one, it's in C, and it's also C hard. Basically, to prove that it's in C hard, you have to prove that it's one in C, and two, you have to prove it's C hard. An example was just what we discussed, and yeah, to prove that it's C complete, you just need to prove that it's in C, and two, it's C hard. In this case, C is NP. The class we are referring to is NP. So just pause for a second and try to define what coNP complete is. Yeah. This is the diagram. We have P, and I told you that P is contained in NP, and we have the NP hard class, and if you have a line of difficulty, this is what it would look like. And we have the NP hard class, and I already told you that all NP hard problems need not be in NP. So, and this, the part where it overlaps, it need not be just a point. The part at which it overlaps is the class NP complete, because this class is an NP and it's also NP hard. So by definition, this is NP and NP hard, so that's making it NP complete. So I hope this is clear. It'll become much more clearer. It'll become clearer after this Venn diagram. I'm assuming P is not equal to NP in the left hand diagram. So we have P, which is contained in NP, which is contained in NP, and we have NP hard, which is actually not entirely in NP, like I already told you, and thus the overlap between NP hard and NP is NP complete. And if someone in the future, it could be you, if someone from future actually proves that P equal to NP, which is unlikely, but if that happens, then this NP collapses to P, because NP equal to NP, that would mean, the whole thing collapses, and thus we have P equal to NP complete, and the whole Venn diagram would become a lot more easier if someone proves that P is equal to NP. So that is the result we have on the right hand side. Yeah, and that is the problem of P equal to NP, P versus NP, and that is like what it means. It's one of the most millennial prize problems. It's by the Clay Institute, and it's the Millennium Prize problems, and it actually can be described simply as this: does being able to quickly verify the solution to a problem mean that we can also quickly solve the problem? Does if we can verify a solution to a problem, does it quickly? Does it also imply that we can solve the problem? So that is the question of P versus NP in a nutshell. We do not know that yet, and all we know is that for now is that P is contained in NP. So if P equal to NP, the whole thing collapses, and we'll have just a circle of sorts, and where NP collapses to P. There are a lot more classes than what I just described, but that captures the basic fundamental classes that are introduced to you in algorithms course. Of course, there's the randomized complexity class. There's P, there's NP. There's RP, there's coRP, there's ZPP, there's BPP, there's L, which is the space complexity classes. L, NL, coNL, and you have a lot more classes like sigma 2, pi 2, and so on. And maybe you can discuss that sometime in the future. This is a very fascinating quote I came across. If P equal to NP, people actually um, talk about things like protein folding algorithms can be solved and quickly, and if those can be solved quickly, we have the cure to cancer, or all these net banking systems, internet banking systems would be prone to hacking, because basically cryptographic algorithms would be easier to crack. So those are very interesting examples, but this quote I found it more succinct, and I found it very interesting. And it's this. It's a quote by Scott Aronson, who's a very popular computer scientist, and he quotes, "If P equal to NP, then the world would be a profoundly different place than we usually assume it to be. There would be no special value in creative leaps, no fundamental gap between solving a problem and recognizing the solution once it's found. Everyone who could appreciate a symphony would be Mozart. Everyone who could follow a step by step argument would be Gauss. Everyone who could recognize a good investment strategy would be Warren Buffett." With that, I conclude, and I would highly recommend you to watch this video. It has beautiful animations, and it captures the idea very well. And it's a video by Hackerdashery on computational complexities. And that's it for today. Have a great day. Bye bye. And thank you for watching.